Hello everyone, this is a little presentation about the differential equations. So we will begin with the definition of a differential equation. So by definition, a differential equation is a relationship between function generally presented as y and its derivatives, noted as y prime, y double prime, so solving a differential equation is to find y. So that is the definition of a differential equation. So there are many type of differential equation, but the most easier to solve and possibly the ones that are solved because other are very difficult to solve. Okay, so the one we can solve are the linear one. What is a linear differential equation? So a linear differential equation is an equation where y prime, y double prime are on the first power, not second power, not third power. So they must be first power. So for example, if I have something like y squared, it's not linear. Okay, so we must have something like y, okay, plus, for example, y prime plus x equals 0, for example. That is a linear equation, not linear. So the linear equation are, we can solve them. Okay, so it is a linear differential equation. Why we can solve them, such equations? Because their solution are also linear. How is that? For example, if I have an equation, I will find some easy equation to begin with. We will begin with the equation that was put it as thumbnail for this video. Okay, so I will begin with the equation of the form y prime plus omega squared, so little omega squared y equals 0. Okay, I will try to solve this one. So beginning, we can try something. What about, for example, I choose y equals sine of omega t, omega x. So I can calculate, here is double prime. So I can calculate y prime. Y prime is also how to calculate the derivative of sine omega x. Is the derivative of omega x, which is omega. The derivative of sine something is cosine. So it is cosine omega x. And then I can calculate omega double prime, y double prime. It is the derivative of the derivative. So here, in second time, omega is the derivative of omega x, chain rule, and the derivative of cosine something is minus sine. So minus omega squared sine omega x. But what is minus omega squared sine omega x? I know that sine omega x is y. So that one is equals to minus omega squared y. So after rearrangement, I can see that omega double prime plus omega squared y equals 0. So it is a solution. So sine omega x is a solution of this differential equation. But is that the only solution? No. We can see that if, for example, I choose y as a constant, for example, a times sine omega x, it is fine. It's also a solution. We can see that nothing changed here. We can put here a. So here we have the a, and here we have the a again. And we can replace a sine omega x by y, and we have the same solution. So it is linear because any linear function of any solution is also a solution. On the other hand, we can see that if I choose y equals, let's say, b cosine omega x, I have the same thing. Y prime equals minus omega b sine omega x, and y double prime equals minus omega squared b cosine omega x. And so I have minus omega squared y. And even this one is a solution. So I can see that omega double prime plus omega squared y equals 0 also. So it is another solution. So in general, I can see that y can be written as the combination of this two solutions, a sine omega x plus b cosine of omega. So that is the general solution for this equation. So that what we call the linearity of differential equation. So if I have two solutions, for example, I can find two particular solutions. The general solution can be written as a linear combination of these two particular solutions. So this is the general solution of this general form. So we can remember that y double prime plus omega squared y equals 0 is a differential equation of second order because we have here a second derivative. So we call this second order equation. So the solution is in this form, y equals a sine omega x plus b cosine omega x. This form is used in mathematics in general. In physics, you can see something similar, also solution of this differential equation. It has this form in general. We write it as this form. So it is y equals y maximum sine or cosine omega x plus something constant, generally called phi. Okay, so it is a similar, another form to write the same thing. Okay, we can prove that. Let's prove that. So how I can transform this form into this form. Okay, in fact, if I take here A and B, I have A and B. So if I called tangent phi equals A over B. So I can say that A equals B tangent phi. And so I replace this A by its value here. I write here B tangent phi tangent phi. And so we can take B in factor and write tangent phi as sine phi over cosine phi. So let's put tangent phi equals B over A. Sorry for that. So B is equals A tangent phi. Here A and B. So now I can take A and as I say it, and write here sine okay okay, and in place of tangent phi I will write sine phi over cosine phi. So it's sine phi over cosine phi. So let's make this an equation. Okay, we will use the same phi here. Okay, now if I take cosine phi, I multiply and divide by cosine phi. So I divide here the A over cosine phi, and here in the factor I have sine omega x, but I multiply it by cosine phi. So I have sine omega x times cosine phi plus sine phi, let's see, cosine omega x sine phi. Let's okay. Okay. So what is this formula? Sine A cosine B plus uh, cosine A sine B. It is sine A plus B. So this one is equals to sine A plus B. Okay, that is the form that we want. So we see that it is similar to the form used in physics. So it is the same form by choosing phi such as tangent phi equals A E over A, and y m equals a over cosine y. So it is the same thing in physics and in mathematics, but in physics they use this form because it is more convenient for their application, because in physics they call the ym amplitude is the maximum value of y, and they called phi the disphasing, okay, and omega is called the pulsation. So they have their application in physics. So these two forms are identical. Now we can take another type of equations and see how to solve them. So we will take another form. This is the form y prime plus, for example, x y equals something we call in general a y and equals 0. How to solve this equation? So we will write y prime as dy over dx. You know, we can do that. So I can write dy over dx equals minus ay, and then I put it as a form dy over y equals minus a dx. Now I can find the primitive of the sides, the two sides. So I can calculate here primitive. So primitive of dy over y and primitive of minus a dx because minus a in this case was a constant. So let's see. The primitive of dy over y is natural logarithm of y. So I have here natural logarithm of y. One became the natural y. Here it is minus ax plus something, a constant, integration constant, plus integration constant k. Now I can put the exponential on the two sides. So this here's the absolute value of y in fact. So if I put the explanation here and here, I have a and to the power ln of absolute value of y and here also I have a to the power that. Okay, so that gives me e and ln are reciprocal functions, so they cancel one with the other, and we have absolute value of y. And so I finally have something like this. So I have here absolute value of y equals this one. But this one can be written as e to the power a times e to the power minus ax. And because we have absolute value here, we can rid of it by plus or minus. So I have here y equals plus or minus. Plus or minus e to the power k can be written as c, a constant. It's an arbitrary constant. So I can rewrite this as y equals c times e to the power minus ax. So it is the general solution of this equation. So that was the introduction to some differential equation. We solved some second order differential equation of the form y double prime plus omega squared y equals 0. We saw that we have seen that the solution is a sine omega x plus b cosine omega x, where a and b are arbitrary constants. And for the equation of the form y prime plus ay equals 0, we have seen that the solution is y equals c exponential of minus ax. So thank you for watching and see you later.